Hello there. In today's video lecture, we are going to deal with section 5 of this chapter, which is dealing with Cauchy's theorem and integral formula. So, in the earlier sections, we had proved that Cauchy's theorem of analytic functions in a disk, that is, if G is an open disk, then integral over gamma f is equal to 0 for any analytic function f on G and any closed rectifiable curve gamma in G. We have proved that. So our question is which is an important question, and the remaining sections of this area, Cauchy's theorem and integral formula, is actually arising from this question. And this question is, for which regions G this result will remain valid? And there are regions for which this result is false. For instance, you can see here if G is the punctured disk punctured at 0, C minus at 0, and suppose if our function is 1 by Z, definitely this 1 by Z is analytic in G. We are defining a closed rectifiable curve gamma, which is gamma of t is equal to e raised to it, where t is varying from 0 to 2 pi. Then we had already proved that integral over gamma f is equal to 2 pi I, which is not equal to 0. So this result is not true in some regions. And definitely you can understand that C minus set 0, you will have a hole in this region. That means the set 0 is being removed, right? So there is a hole there. So integral over gamma f is equal to 0 for every analytic function f, it is satisfied, and for every closed rectifiable curve gamma in regions G, which doesn't have any hole. So that is actually the idea of the whole section. And here we are having a different approach. We are fixing a region G and an analytic function f on G, and seeing is there any condition on the closed rectifiable curve gamma such that integral over gamma f is equal to 0. So all the discussions which we made now can be seen in the coming theorems and lemmas. So the first lemma is, suppose if gamma is a rectifiable curve and suppose phi is a function defined and continuous on set gamma. For each m greater than or equal to 1, we are defining a function fm of z is equal to integral over gamma phi of w into w minus z the whole raised to minus m dw for set belongs to set gamma. Set doesn't belong to set gamma. So we are defining this function fm of z for all z which are not coming as points on gamma. Then each fm is analytic on c minus z gamma, and the derivative of that function fm dash of z is equal to m into fm plus 1 of z. So this is our aim. So we have to prove that the function defined fm is analytic on c minus set gamma. For that, our first claim is that fm is continuous. So let's prove that fm is continuous. So we are fixing an element a naught belonging to the gamma, and suppose if small r is equal to the distance of this point a to the curve gamma. That means that will be the least distance between the points of gamma to A. Okay, and suppose if B is a point on C which is satisfying the condition modulus of A minus B is strictly less than delta, which is strictly less than R by 2. Then fm of A minus fm of B is considered. That is equal to, by the definition we know, integral over gamma phi of w divided by w minus A the whole raised to m dw minus integral over gamma phi of w divided by w minus B the whole raised to m dw, which is equal to, on rearrangement you get integral over gamma phi of w into 1 by w minus a the whole raised to m minus 1 by w minus b the whole raised to m dw. And we know that a raised to m minus b raised to m is equal to a minus b into a raised to m minus 1 plus a raised to m minus 2 into b plus a raised to m minus 3 into b square plus etc plus a raised to 1 into b raised to m minus 2 plus b raised to m minus 1. So using this formula, we can apply that on this term, and that term will automatically become this. So you get integral over gamma phi of w is phi of w into 1 by w minus a minus 1 by w minus b into summation k is equal to 1 to m 1 by w minus a raised to k minus 1 1 by w minus b raised to m minus k dw. So here you can see that in this formula you could see each of the term in this braces will have a total degree m minus 1. Here it is m minus 1, here it is m minus 2 plus 1. So you have m minus 1, here if you have m minus 3 plus 2 you have m minus 1 and so on. So in total when you do the summation here k minus 1 plus m minus k will give you m minus 1. So again on rearrangement you get integral over gamma phi of w into a minus b divided by w minus a into w minus b into summation k is equal to 1 to m 1 by w minus a the whole raised to k minus 1 into w minus b the whole raised to m minus k dw. And that is equal to you can take the w minus a and w minus b into the summation, you get integral over gamma phi of w into a minus b into summation k is equal to 1 to m 1 divided by w minus a the whole raised to k into w minus b the whole raised to m minus k plus 1 into dw. And so in total you are getting fm of a minus fm of b is equal to integral over gamma phi of w into a minus b into 1 by w minus a into w minus b the whole raised to m plus 1 by w minus a the whole square into w minus b the whole raised to m minus 1 plus etc plus 1 by w minus a the whole raised to m into w minus b the whole into dw. So you can call it equation star. And here modulus of a minus b is strictly less than r by 2 and w is coming from the curve gamma, and we have modulus of w minus a is greater than or equal to r strictly greater than r by 2 and modulus of w minus b is greater than or equal to r strictly greater than r by 2. All these conditions are satisfied here according to the values we have taken for A and B and W coming from this curve gamma. So this is satisfied. So you can apply all these things, applying the modulus on Fm of A minus Fm of B. This is less than or equal to that will become less than or equal to, because you are taking the modulus inside the integral, you get something like this. And then instead of this modulus of phi of w, you can take the maximum of modulus of phi of w, where w is coming from the curve gamma, and 1 by modulus of w minus a will be uh, strictly less than yes, here we have modulus of w minus a is greater than or equal to r by 2. So 1 by modulus of w minus a is coming here. So you have it to be r by 2, and here also you have r by 2 the whole raised to m, and likewise you can give the inequality each for each term, and then you can just add all the terms together, because the denominator you have r by 2 the whole raised to m plus 1 coming for each of the term, and there will be m terms coming here. So you have m by r by 2 the whole raised to m plus 1 for this term inside the braces. Instead of the term in the braces, you can have this term into modulus of dw. And definitely, since the integration is happening with respect to w, this modulus of a minus b can be taken outside the integral, and all. Since we are taking the maximum of this, that can also be taken outside the integral into this is a constant, it can be taken outside, then you have integral over gamma modulus of dw, which is nothing but the total variation of this gamma, which is denoted by v of gamma, which we had seen while we were starting the Riemann stages integral section. We had defined what is total variation and the properties related to that. So finally, you are obtaining something like this. Okay, so suppose if so we want to prove that this fm is continuous. So suppose if this epsilon is greater than 0 be given, we have to choose a delta greater than 0 such that delta is less than both r by 2 and the term sitting here, which you can see which is closely associated to this. Just take reciprocals and rearrange to find how this comes. Okay. So if delta is like that, definitely whenever modulus of a minus b is strictly less than delta, modulus of fm of a minus fm of b is strictly less than epsilon. So this means that fm is continuous. So we prove that. Now we have to prove the rest of the theorem, which says that the function is analytic and the derivative is so and so. So if we prove that, we already proved it is continuous, and if we prove that its derivative is so and so, we can conclude that it is analytic. So for that, we are fixing an a in C minus set 0. Let set belongs to G and set not equal to a. Then Fm of Z minus Fm of A divided by set minus A is considered. The terms are written expanded with respect to the definition of this Fm of A. Fm of Z is defined to be uh, integral over gamma phi of w divided by w minus z the whole raised to m. Here you can get this result from, we had named an equation star from here. Okay, so instead of in this equation you have a and b. So instead of b you will have to replace the value with a, and instead of a you will replace with z and write the equation. Hope you are able to understand that we have replaced this equation star. We have already this equation star happening, and we are replacing this a with z and b with a. That's it. So you are obtaining this equation sitting here. Okay, suppose if this in this equation this phi of w divided by w minus a. This is the numerator of each of the term. Phi of w divided by w minus a, phi of w divided by w minus a the whole square, etc. Phi of w divided by w minus a the whole raised to m, like that. So since this a is coming from C minus set gamma, definitely this function phi of w divided by w minus say the whole raised to k, for k is equal to 1 to m, will be continuous on set gamma for each k. Okay, so you can treat this phi of w into w, phi of w divided by w minus a the whole raised to k as phi itself. Like think of phi absorbing the powers of w minus a. Okay, that is you can think of phi of w to be phi of w into phi of w into w minus a the whole raised to minus k. Think like that. Okay, so if we think like that, this equation, you need not rewrite it in your lecture notebook, you just think like that. If we are able to replace the numerators like that, you can, if it is absorbing, you get the equation to be integral over gamma p of w divided by w minus z the whole raised to m dw plus etc plus integral over gamma p of w divided by w minus z dw. Right. So this actually was proved in the first part of the theorem that fm of z is continuous. That is integral over gamma p of w divided by w minus z the whole raised to m is continuous whenever the numerator function is continuous. So here the numerator function, all of them are continuous. So each of them will be continuous, right? So everything which is on the right hand side is a continuous function, right? So you have this to be a continuous function and you are going to let set tends to a on both sides. Okay, now you got this function is continuous, RHS is continuous, definitely LHS is continuous. Make set approach a. When set is made to approach a, you have limit set tends to a fm of z minus fm of a divided by set minus a to be becoming the derivative of fm at a, that is fm dash of a. So the left hand side becomes fm dash of a, and on the right hand side you had just thought about like that. Okay, so you have this and you are tending set tends to a, right? So when z is 10 to a, each of the term where z is happening, you substitute it with a, and you already have a w minus a, and here you have w minus a the whole raised to m, and this will come to the denominator, and that will be w minus a the whole raised to m plus 1. That will happen for each term. So you have m such terms happening on the right hand side, which all are the same. So you, and each of the term are nothing but fm plus 1 of a by a definition of fm of z, right? So you are adding m of them and you get m into fm plus 1 of a, which is what we need to conclude in the lemma. Now we are moving into Cauchy's integral formula, first version. The statement says that let G be an open subset of the plane and f from G to C be an analytic function. Gamma is a closed rectifiable curve in G such that n gamma W is equal to 0 for all W in C minus G. Then for A in G minus set gamma, n gamma A f of A is equal to 1 by 2 pi I integral over gamma f of G divided by set minus A dz. So you just have to prove this equation under the given hypothesis. So you are given G open set, F to be analytic function from that open set, and if gamma is a closed rectifiable curve such that uh, for every W that is happening outside, that is outside this G, that is C minus G, for every W, n gamma W is equal to 0. If all this happens and if A is in G minus set gamma, prove this. For that, define first phi from G cross G to C, which is phi of set W is equal to f of set minus f of W divided by set minus W whenever W is not equal to Z. That is possible to define like that, and it is analytic. And for W equal to Z, for W equal to Z, define phi set Z is equal to f dash of Z. Fine. Why we can define f dash of z? Because we are given that f is analytic function. So we don't have any problem defining like that. And this function which we define now is a continuous function. Because yes, this is a function and this is the limit of that function. So that will be continuous, obviously. Okay, and for each w that is happening inside G, this z is map to phi of set W. That is actually an analytic function also. You have to prove that it is an analytic function. It is left out as an exercise. Please do it. It is very easy to prove. Definitely it is continuous. You just have to prove that it is analytic also. Okay. Now let H be a set such that W's are in C such that n gamma W is equal to 0. The winding numbers, set of all the complex numbers such that the winding numbers about gamma is equal to 0. We know that winding number n gamma W is always an integer valued function. Okay. And as this n gamma w is equal to 1 by 2 pi I integral over gamma 1 by z minus w dz. That's how we define, right? So in the in the lemma which we had talked about earlier, we said that integral over gamma, a function which is continuous in the denominator divided by z minus w, the whole raised to any power, any integral power dz will be a continuous function. So definitely one is a continuous function. So integral over gamma 1 divided by z minus w dz will be a continuous function upon the hypothesis. All the hypotheses of the lemma are satisfied here. Check it out. So you have it to be continuous and integer value. Okay, so h n being a function, right? So you can treat it like this. Suppose this h is equal to set of all w belongs to C. I'm treating this n as a function. So f of w is equal to 0, right? So you can think about f inverse of, so or this this h can be written as f inverse of set 0. Okay, so here this function h, so it is becoming an open set. Okay, so because it is the set of all points where 0 happens to be, so definitely that will be outside this gamma, and that will be an open set. Okay, because it is a continuous function. And from the hypothesis, you can understand that H and G, when you take the union of that, that will be the whole complex plane. Define a new function G from C to C such that G of Z is equal to integral over gamma phi of Z W dW if Z belongs to G, and if z belongs to H, define g of z is equal to integral over gamma 1 by w minus z into f of w dw. Hope the definition of this g is clear. So you had earlier noted that C is equal to H union G. So you define a function for elements in G and you defined a function for elements in H. So for this function to be well defined, we have to assert that the points inside the intersection will give equality of the both definitions in the sets G and H, right? So you are taking integral over gamma phi of ZW dW, which is the definition of G of Z in G, right? Then you know that phi of ZW is nothing but f of W minus f of Z divided by W minus Z, right? Over the integral gamma. That is equal to integral over gamma, you split it up. Integral over gamma f of W divided by W minus Z dW minus f of z can be taken out because we are integrating with respect to w. So integral over gamma 1 by w minus z dw. But this is nothing but the from the definition of winding number that can be written as 2 pi I into n gamma z. Just cross multiply and rearrange. But we know that n gamma z is happening to be 0 from the definition because z is belonging to H, and all the elements inside H will have the corresponding index or winding number to be 0. So you get this is equal to this. So you have for every element inside the intersection, both definition, both this and the function here, both are equal. So you have G to be a well-defined function. Okay. Now, by lemma 5.1, okay, by lemma 5.1, we are getting that G is an analytic function definitely, because we know from the hypothesis that continuous, F is continuous, and all the hypotheses of lemma 5.1 is are satisfied. So integral over gamma f of w divided by w minus z dw is an is analytic is analytic by lemma 5.1, and also definitely g of z, which is defined inside G, that is integral over gamma f of w minus f of z divided by w minus z, that is also analytic. So you can see this g of z is equal to, which is g of z is equal to integral over gamma f of z minus f of w divided by z minus w dw, where z belongs to G, and integral over gamma f of w divided by w minus z dz, where z belongs to H. So this is an entire function. Why? Because f is analytic by lemma 5.1. That will imply G is analytic in both G and H, but G union H is C, so G is analytic inside C, so that will be entire. Now, theorem 4.4 says about H being an unbounded component of G. You can just read through the theorem 4.4, what it says. So, here this H being in the unbounded component of G, it will definitely contain a neighborhood of the point infinity, which in the extended complex plane. And also our set gamma is a compact set, that is our curve. The set of points in the curve is a compact set. So that will imply that the set is bounded on our gamma, that this f, the function f is bounded on our set gamma, and also that limit set tends to infinity, 1 by w minus z is equal to 0. That happens uniformly for w in set gamma. Limit, so from that you can move to limit set tends to infinity g of z is equal to limit set tends to infinity integral over gamma f of w divided by w minus z dw, which is equal to integral over gamma limit set tends to infinity f of w divided by w minus z dw, because here we are talking about uniform convergence, so you can take the limits in, and that is equal to integral over gamma f of w into limit set tends to infinity 1 by w minus z dw, which is nothing but 0. So you got this limit set tends to infinity g of z is equal to 0. G tends to infinity, g of z is equal to 0. That means there exists an r strictly greater than 0, such that modulus of g minus 0 less than or equal to 1 whenever modulus of this said minus 0 is greater than or equal to r. This is actually just the definition of limit set tends to infinity with epsilon taken as 1. Now, since B bar is nothing but the closed ball centered at 0 with radius r. It is actually a compact set. So G being analytic and it is on a compact set or rather it is continuous. In particular, G is continuous. So continuous function on a compact set will be bounded. So G is bounded on this B bar of 0 r. It follows that G is bounded an entire and by Liouville's theorem G will be a constant. And from this statement, limit z tends to infinity, g of z is equal to 0, right? So g being constant, the only possibility is that g should be identically 0. Otherwise, this will not happen. So if a belongs to g minus set gamma, then we know that g of a is equal to 0 because g is identically 0. So then what is g of a? G of a will be it is already defined as integral over gamma f of z minus f of a divided by z minus a dz. Okay, and that is equal to, you split it out, you get integral over gamma f of z divided by z minus a dz minus f of a into integral over gamma dz divided by z minus a, which is equal to integral over gamma f of z divided by z minus a uh, minus f of a into n gamma a 2 pi I, which is coming from the definition of the index of the curve gamma with respect to the point A. So you are done with the theorem which says that n gamma a into f of a is equal to 1 by 2 pi I integral over gamma f of z divided by z minus a dz. And in Cauchy's integral formula second version, you just have a modification of the hypothesis where again G is an open subset of the plane, F is an analytic function from G to C, and you have some M closed rectifiable curves named gamma 1, gamma 2, etc., gamma M, such that n gamma 1 w plus etc. plus n gamma m w is equal to 0 for every w in C minus G, and for all A belongs to G minus set gamma, you have the statement to be f of A into summation k is equal to 1 to m n gamma k A is equal to summation k is equal to 1 to m 1 by 2 pi I integral over gamma k f of k divided by z minus a dz. So this actually follows from the theorem which we said now, which is Cauchy's integral formula first version. The same steps follow here. Here just define GZW as it was defined earlier. And here the difference is when you define H, here the H will be set of all W belongs to C such that the summation of the index, the winding numbers will be equal to 0, and define, now that G of Z is defined like that, except the sum of integrals over gamma 1 etc gamma m are coming into picture, everything is the same. So you can work out the details of the proof of the second version by just following the steps from the first version and prove out the same. Now comes Cauchy's theorem, first version. This theorem states that if we are given G, which is an open set of the plane, and f from G to C to be an analytic function, if gamma 1 etc. gamma m are closed rectifiable curves in G such that n gamma 1 W plus etc. plus n gamma mw is equal to 0 for all w in C minus G, then summation k is equal to 1 to m integral over gamma k f is equal to 0. Here you don't have anything to do but just in this Cauchy's integral formula second version, you just think that f of z is nothing but f of z into z minus a. That is also applicable, right? That function is also satisfying the hypothesis. So wherever there is f of z, substitute it with f of z into z minus a. So here f of a will be f of a into a minus a, right? Into summation k is equal to 0 to m n gamma k a, that is equal to summation k is equal to 1 to m 1 by 2 pi I integral over gamma f of z into z minus a. See, wherever there is f of z, you replace it with f of z into z minus a into dz. So you cancel them out. So what remains is this, left side will be 0. This 1 by 2 pi I can be taken out, that will just vanish, and you get what is required in Cauchy's theorem, first version. And you can just read through what is said about this in between the Cauchy's theorem and the next theorem. Okay, theorem 5.8 says that let G be an open subset of the plane and f from G to C be an analytic function. If gamma 1 etc. gamma m are closed rectifiable curves in G such that n gamma 1 of W plus etc. plus n gamma m W is equal to 0 for all W in C minus G, then for A belongs to G minus set gamma and k greater than or equal to 1, Fk of A summation j is equal to 1 to m n gamma j A is equal to k factorial into summation j is equal to 1 to m 1 by 2 pi I integral over gamma j f of z divided by set minus a the whole raised to k plus 1 dz. So here we just have to differentiate k times with respect to the variable a, what we have obtained in the first version of Cauchy's integral formula. When you differentiate with respect to a, what you obtain is this. The first, when you differentiate the Cauchy's integral formula with respect to a k times, you get the equation sitting here. And since the summation j is equal to 1 to m n gamma j is constant, you can repeat the lemma which we mentioned at the first on it to simultaneously prove the statement we need to prove in theorem 5.8. And theorem 5.9 is just a particular case of theorem 5.8, corollary 5.9, because here we just have one closed rectifiable curve. Here you had some finite number such that the indexes are summation is equal to 0. Here there is only one closed rectifiable curve such that its winding number or the index is equal to 0 at W for all W belongs to C minus G. Then you just rephrase what you have here. That's it. So now comes Morera's theorem, which is the last portion of this section. This Morera's theorem actually gives a statement. Suppose if G is a region and f from G to C be a continuous function such that integral over T f is equal to 0 for every triangular path T in G, then f is analytic in G. So this triangular path is nothing but a closed path such that it is actually a polygonal path and it has three sides. So you know what's a triangle is. So actually this can be treated as a converse part of the Cauchy's theorem which we mentioned now. That is whenever you have integral over Tf is equal to 0 for every triangular path T in G, then f is analytic. Earlier we said that if f is analytic, integral over gamma f is equal to 0 for every closed rectifiable path coming inside the region we are considering. So actually Morera's theorem is a kind of converse for Cauchy's theorem. And sometimes this Cauchy's theorem is also called Cauchy-Grossack theorem. So let's move on to the proof. So we have to prove that f is analytic. So our claim is that this small f has a primitive capital F. Primitive is nothing but antiderivative or integral of small f. So if we claim this, we can understand that capital F dash is equal to small f. Okay. So we have to show that show this happens in capital G, which is a region which is open connected. So we are going to basically prove it for each open disk inside G. So we are done with that. So we are going to show that F is analytic on each open disk inside G. So instead of G, I am assuming that G is an open disk. So that will be done. So suppose if G is equal to BAR. So we are going to prove that f as a primitive. So for z in G, define capital F of z is equal to integral over closed a z f. Okay, that is closed a z means the closed interval a z f. Now fix z naught in G. Then for any point z in G, the hypothesis will imply that f of z is equal to integral over closed A set naught F plus integral over closed set naught Z F. So definitely f of z minus f of set naught is equal to integral over A set naught plus integral over set naught Z minus integral over A set naught. So you get integral over set naught set F. So that's what we have here. Therefore f of z minus f of set naught divided by z minus set naught will be this. Okay, now consider f of z minus f of z naught divided by z minus z naught minus f of z naught. So that can be, this f of z naught can be taken inside the integrals. F of, this is actually, this one is actually 1 by z minus z naught into integral z naught z f. And this f of z naught is taken inside the integral. How? If we integrate it, f of z naught is a constant. So you get f of z naught is taken outside, then you integrate with respect to z from z naught to z, you get z minus z naught when you integrate. And in the denominator also you have z minus z naught. You can check this out. This is what we are saying. So when you integrate this term, you can take the f of z naught out, then integrate z naught z with respect to dz. You get that to be z minus z naught, and that will cancel out. So what is written here is correct. Okay. So that is equal to 1 by z minus z naught integral over set naught z f of w minus f of set naught dw. Now you are taking the modulus sign here. When you take modulus, you get you can take modulus here, and this the modulus comes inside mod dw, and you can take this modulus of f of w minus f of f of set naught out. When you integrate, you just can take that out, and then you have integral set naught to set dw to become, when you integrate you get set minus set naught. So this one and that one will be cancelled out, the modulus signs. So what remains is when you integrate you get f modulus of f of z minus f of set naught here. Okay, this is what you obtain from this when you apply the modulus. So then what you have to do is you have to approach z to set naught. So what happens is in the right hand side you will have 0. So in the left hand side that will mean limit z tends to set naught, f of z minus f of set naught is f of set naught divided by z minus set naught is equal to f of set naught. That is f capital F dash of set naught is equal to small f of set naught. Or we can say that capital F dash is equal to small f. That means f is analytic. So that's Morera's theorem. Please go through all the theorems and lemmas and outline of the proofs which we said, and do write down the lecture notes and make everything clear by yourself. So thank you for watching out. See you in the next video lecture.